Is about infinite state systems and compilation, and the speaker is Enrico Maniago. Enrico, are you around?
Yes, I'm here.
Okay. You want to share your slide?
Sure.
Okay.
So I hope everyone can see the slides.
Yes, I can see them at least.
Fine. So good afternoon, everyone. So I'm going to present you our work titled Proving the Existence of Fair Paths in Infinite State Systems. So the problem we are dealing with in this paper is trying to identify and represent fair paths in a transition system. In particular, we are interested in infinite state system. So this problem in this context is undecidable. One thing that is commonly done to identify such a path is look for lasso-shaped paths. This, of course, is not sufficient in infinite state, and we need some ways to identify and represent paths with different shapes. What we propose is to represent them using a structure that we call R abstraction, which is a reachable non-empty under approximation of our transition system that contains only fair paths. So here I'm showing you an example of an R abstraction that can be used to represent a set of fair paths of these very simple code that is encoded also as this SMD model as a transition system. So what are the main features of this abstraction? So it has a sequence of regions, one of which must contain only fair states. So one region must be a fair region. Then we have a transition relation that can allow some bounded dwell on some region, but must eventually ensure progress towards the fair region. So this abstraction can be seen as a generalization of a technique called a closed recurrent set for the setting in which we have some fairness condition. In this work, we propose to search this abstraction compositionally. So we look for an abstraction that can be identified as a composition of some smaller components that we call the AG skeletons. And we propose a procedure that, given a set of these components, these skeletons, it looks for one such abstraction. So what are these G skeletons? Each G skeleton is actually another transition system, which is responsible for a subset of the symbols. And this means that its transition relation is providing us with the constraints that allow us to compute the next value assignments for these symbols. And again, is a transition system that has a sequence of regions. And each region has an invariant and some assumptions. So the transition relation must ensure that the invariant holds, and the assumptions are constraints over the other symbols, the one for which the current AG skeleton is not responsible for. So here on the slides, I'm showing you some examples of possible AG skeletons we might define for the same code we are looking at before. So the hypothesis we have on these AG skeletons is that if the transition relation maps a state in some region I into a state in some region J, then every state in region I must have a successor in region J. So this is the main assumption we have on these structures. And for the composition, we do the synchronous product between these skeletons, but the synchronous product must ensure that the assumptions of each G skeleton are met. So this gives us another AG skeleton. So we show that the composition operator is closed with respect to the set of AG skeletons. But we end up with a transition system that may or may not be an under approximation of our original system, may or may not be reachable, and we don't know if it contains a fair region. So our objective then is to find a reachable composition of these AG skeletons that allows a loop over the regions, one of which should be fair, and each transition in this loop over the region must be an under approximation of the transition relation of the original transition system we were looking at. And if we are able to find such a loop over the regions, then this is our error abstraction we are looking for. So this is pseudocode showing a possible way to implement this search procedure. And the inputs are our original fair transition system M and a sequence of AG skeletons H. So the first thing the procedure does, it checks whether the input AG skeletons meet our hypothesis. Here it's filtering out all the ones that do not. Then it moves on to the main loop of the procedure, in which we propose a reduction to a reachability problem to extract possible candidate compositions. So here we encode our search for the abstraction into a reachability problem, and then we use an off-the-shelf model checker to find a path. In our case, we are using Nextend to solve this problem. Then from these trace, we can get a candidate composition, and by the encoding into reachability, we know that this candidate composition is reachable, it's an under approximation, it has a loop over the region, one of which is fair, but it does not guarantee that the assumptions of the AG skeletons are met. So we check this on line 12, and if this is the case, then we are done. We found our error abstraction. Otherwise, we learn a conflict, meaning a set of regions and transitions that do not meet some assumption. And we use this information to refine the reachability problem we generate at the next iteration so that we do not repeat the same error. And we do this until either we find an error abstraction or we find that the model checker is unable to provide us with a trace, in which case we return unknown. So we wanted to apply this technique also to timed and hybrid systems. And in these settings, we must ensure that our infinite fair path is non-zero, meaning it allows the time to diverge. And we propose two ways to do this. One is local to an AG skeleton. So if we are able to provide that in an AG skeleton in isolation by itself, time can diverge, then we are guaranteed by the composition operator that every composition we came up with that uses these AG skeletons preserves this property. So we generate only AG skeletons in which time is allowed to diverge. But it might be the case that the local information of a single AG skeleton is not sufficient to conclude anything about the divergence of time. So we provide a set of sufficient conditions under which it is possible to shrink the language of either an AG skeletons or error abstraction, such that we rule out all xenopaths, but we do not make the language empty. So we end up with a structure, an error abstraction that has at least one path, and we know by this restriction that this path will be non-zero. So this allows us to also provide this additional property that is necessary when dealing with timed or hybrid systems. So we implemented this in a prototype and performed some experimental evaluation. We considered 31 nonlinear software benchmark that we took from the paper that is mentioned there on the slide. We consider 3 infinite state systems and 9 hybrid systems. So we compared here with 3 automated tools. So the input to the procedure is different. So these are automated tools, while our procedure needs the user to provide these lists of skeletons. So the focus here is not much on how much time do each tool take, but we wanted to see whether our benchmarks are significant, meaning here we can see that the automated tools are unable to provide definite answers in some cases, while our procedure is able to identify an error abstraction in each of them. So then what we did was to look at how much does our procedure scale with respect to an increasing number of these skeletons. This means that we are making the search space for our error abstraction bigger. So we considered 3 benchmarks. One is one of the software benchmark. The other one is one of the nonlinear transition system, infinite state transition system. And the last one is an hybrid system. We increased the number of skeletons we provide to our procedure, and we look at how much this affects the total runtime. So in summary, we have seen how we can represent a non-empty set of fair paths using the structure we call error abstraction. We have seen an automated search procedure for this error abstraction that, given a sequence of skeletons, it looks for an error abstraction. We have seen how we can prove non-zeroness over these structures. And as a future work, the main focus is about increasing the automation of the procedure. So in particular, we would like to have some automated technique to synthesize these skeletons, and then automating the proof of the non-zeroness. And another direction is to allow the synthesis of this error abstraction without assuming a fixed bound on the dwell time on each region. So this concludes my presentation. Thank you very much for your attention.
Thank you very much. If anyone has a question, please just unmute yourself and ask the question. I have quite a technical question. When you have a transition between regions, you have it only if every state in one transition has a transition to, in one region, have a transition to a state in the other transition. This sounds like by simulation. So how do you get the under approximation?
Okay, so here we have the assumption. So the skeleton does not assume anything about the transition relation of our original system. So for example, I might have a non-deterministic assignment in my original transition system, while in my skeletons I specify, I don't know, a specific relation between the current and next value for my assignment. So in this sense, I get, for example, an under approximation.
Okay, thank you very much. Any other questions?
Hi, this is Kedar. My question is about the experiments that you did, like comparing with the other tools. So I'm curious whether the kinds of hints that you provided to your procedure are similar to the sorts of analysis that is done by these tools. I mean, they must also, they're completely automated, but they must also work over a space of regions somehow. So are you describing them in the same way, or are they different?
They are kind of different in the sense that, for example, what Anand does, which is one of the tools here, is basically trying to synthesize the closed recurrent set. So this is a tool meant mostly for software non-termination. So what it tries to do is trying to say that your execution remains within a closed region, a single region.
Mm-hmm.
So in this sense, you might think of our error abstraction as this single region. So as I said before, our error abstraction can be thought of as a generalization of these closed recurrent sets. Mm-hmm. And the main issue here is that since we are dealing with fairness, I need some way to say that eventually I must reach this subset of states. I cannot do that easily with closed recurrent sets. And with respect to the G-skeletons, so our hope to increase the automation is to take inspiration from current techniques that exist, for example, for integer linear loops or other subclasses that identify some non-termination argument and try to use them to synthesize these G-skeletons. Then later we can use to compose. So I hope I answered your question.
Thank you. Yeah.
Thank you very much. Let's thank the speaker again, whichever way we can. And we go on to the next speaker. The next speaker is Anton Xu. Or are you giving the talk there?
No, Anton's giving the talk.
No, okay.
Okay, shall I share screen?
Mm-hmm.
Okay, are we all ready? So are we all ready?
Yes.
Okay, hello everyone. My name is Anton. I am currently a PhD student at the University of Pennsylvania. And today I will be presenting our work on a self-certifying compilation framework for WebAssembly. And this is jointly with Kedarnam Joshi from Nokia Bell Labs. And this is work done during a summer internship. So the crux of this talk asks the question of, how does one write correct software? And in the PL community, we think we know the answer to this, and it looks something like this. So you start with formal logic, then you have formal specification, formal proofs, and formal verification. And in the logical limit of this, you get calc. But in this talk, I want to present another idea towards writing correct software. And more precisely, I will be talking about self-certified compiler optimizations for WebAssembly. So first, I will be talking about exactly what self-certification is. Then I will give a quick rundown of WebAssembly. And finally, I will present our contributions, which include the implementation of a refinement checker, various self-certified compiler optimizations for WebAssembly, as well as evaluation against real-world code. Furthermore, our work is open source at the following link. This will be available at the end, and you can contact me afterwards with questions. All right, so let's get started. So to begin with, what is self-certification? Now, in a typical software execution, you might have a program that takes input to some output. And in contrast with in a self-certified setting, there's some major differences. The first being that the output is now coupled with a witness, and this is also known as a proof or certificate in the literature. In addition, there's a checker that takes this triple of the input, output, and witness, and outputs if it's correct or not. And along with all of this is an underlying theorem that if the checker is happy, then the program has behaved correctly on this particular input. And I want to emphasize that this is not a new concept. You've seen this with things like SAT solvers, where if the SAT solver returns SAT, then a proof or witness will be the satisfying assignment of the variables. And in fact, this naturally extends to any NP problem, and it also arises in the context of model checking, as well as for compilers. Now, in the context of compiler optimizations, the pipeline will look something like this. So first, you have a compiler optimization that takes your source code to some optimized code. And along with this, it spits out an equivalence proof, which is then passed to a backend checker. And this checker can then choose to either accept or reject this optimization as being correct or not. So as an example, we're going to be looking at the SSA transformation. And for you non-compiler people in the audience, all you have to really know are the following. Is that first of all, this is an important optimization for compilers. But it mostly amounts to a renaming transformation where every variable is initialized at most once and must be defined before it's used. So fairly simple, or looks fairly simple, but implementation can actually be fairly complex. And as a consequence, it's a benchmark for formal verification And the proofs here are hard because in something like Coq, you would try to prove correctness of the SSA algorithm for all programs. However, for an individual program basis, if you only want to prove correctness between one program and its optimized form, the proof would actually be fairly simple, as we would see in a bit. So as an example, let's consider these two programs on the in control flow graph representation on the left, and it's SSA transformed on the right. And at first glance, there's two major differences for the program on the right, namely that a lot of variables have been renamed, hence SSA. And there's also this weird phi function at the second to last block, which I'll get to in a bit. But disregarding the phi function, it should be fairly obvious that when you get to the print statement, what's printed on the left should be equal to what's printed on the right. So how might you go about proving this? And the idea is that if we can map equivalences between the optimized program and the source program in such a way that you can establish a connection of x and x not being equal and y3 being equal, then you're all good to go. So let's start from the top end, try to prove this thing. So at the top, you want to assert something like p equals to p. After all, this is the argument to your function. And at this particular branch, you want to assert something like x equals to x naught and y equals to y naught. And you can make a similar assertion at this particular branch. Now, at this point, after doing some SSA, you want to say that y equals to y2, and you still maintain that x equals to x naught. And just after the phi function, you want to assert that x equals to x naught and y equals to y3. And these are the main assertion points that you want to prove. And if you're able to assert this and prove it, then your print function will be equal. And finally, at the end, we add the same assertion for completeness. Now, the green text and the arrows here would correspond to the proofs or assertions that you want to check in the backend. And in the backend, there's a symbolic execution engine to deal with the actual execution semantics of this, let's say like assignment, basic arithmetics, Boolean condition testing, and also for the phi function. So now you've seen how self-certification might look in the context of optimizations, and let's jump into WebAssembly. So first of all, what is WebAssembly? Well, the punchline is this. WebAssembly lets you compile your favorite language to run in the browser. And more concretely, it's a binary instruction set for a stack-based virtual machine that is native to your browser, and is primarily intended as a compilation target rather than something you write in, such as JavaScript. And more interestingly for us, it's a language that comes designed with formal semantics, which takes a lot of the guesswork and assumptions you need to make out of tool building. And just to get a quick glimpse of WebAssembly, since we're all PL people in the audience, I thought it'd be just easier to show you the instruction set. And it looks something like this. And this is taken from the reference interpreter on GitHub. So at the very top, you have some operations for stack manipulation. And you also have some operations for structured control flow, some operations for getting and setting variables, as well as modifying the memory. And finally, some operations for math. So like all this looks fairly standard, and it's a fairly simple language. And all this works over a stack machine, although people will tell you that WebAssembly is technically not a stack machine. I mean, yes, but it's a really glorified stack machine. Okay, cool. So you have a new compile target in a browser. Like, why do you care, right? So, I mean, the thing is that when you have code that runs in a browser with an actively growing code base and user base, and a lot of it being unverified, what does this mean? Really, it means job security. And the truth of the matter is that even for reliable compilers like GCC, you have a lot of bugs. Like here's this Bugzilla page. But with WebAssembly having been introduced, let's jump back into this picture, slightly augmented from before. So on the left here, you have some CFG to CFG optimizations for WebAssembly. And the orange highlights here denote the two corresponding sections in the source and optimized program as to the highlighted program sections, purple sections. So like before, you take a source and you spit out an output in addition to a proof. And this proof would contain an equivalence proof for the orange section, as well as an equivalence proof for the purple section. And this would then be passed to a backend checker. And we use Z3 as the backend SMT checker. Now for division of labor, this part would really correspond to something the compiler writer would do. The compiler writer is the one that is interested in writing the self-certified optimizations, as well as generating the proofs to be checked by a backend checker. And the verifier is then responsible for taking these proofs, as well as the source program and the output program, and comparing them and checking the proof for correctness. And it should be noted that the verifier is write once, reuse many times. whereas you would need to write a new optimization for each optimization that you would want to implement. Okay, so what needs to be done to make this happen? And we had to play all three roles of the verifier, the compiler writer, as well as an evaluator to determine to implement this entire pipeline. So the verifier wants to check proof correctness. And to do this, we need to primarily encode the WebAssembly semantics into logical formulas that can be checked that can be checked by SMT solver. The compiler writer wants to write the optimizations and generate proofs of correctness. And for this, we actually need to go about designing the equivalence proofs, as well as writing some optimizations to back it up. And finally, the evaluator wants to see if this is actually effective and scalable. And we do run this on some real world code. Okay, so for the first task of semantics, WebAssembly is, for all intents and purposes, a stack machine. Variables can either be local or global values, can be either stored locally or globally. The memory array is fairly simple. It's just a linear memory array. And instructions manipulate values on the stack. And for an encoding, we use the theory of arrays and bit vectors. Although for some transformations like SSA, you're able to get away with the theory of arrays and uninterpreted functions, and this will significantly speed up the solving process. So for designing proofs, you've seen this high-level view of the optimization before, and the compiler writer is really responsible for, first of all, instrumenting the code to generate the proofs, as well as writing the optimizations themselves, as well as deciding what parts on the CFG do you want to prove equivalences of. And because we use symbolic execution in the backend, the proofs end up looking fairly simple. And it's just they should identify which path pairs in the source and target, or like the source and optimized WebAssembly should be equivalent. And they should identify what they care about proving equivalence on. For instance, you might care about equivalence modulo what the global memory looks like. So in terms of what we've implemented the following optimizations with their corresponding line counts. And you can see that the proof generation part for is for most of these a relatively small fraction of the entire lines of code. And in particular, you see things like SSA. It's even though it looks like a simple transformation, it actually takes a lot of effort to actually write this. So finally, for validation benchmarks, we use two different data sets. We use the WebAssembly reference interpreters benchmarks, and we also use the WebP image library, which is a C library that can be compiled to WebAssembly using mscripten. And basically, for each function that was present, we first extract the CFG, and then we run on one of the following optimization passes. And this is a table of results for the reference interpreter. So the first column is the optimizations that we ran. The second time is the amount of time we spent on Z3 as a percentage of the total time. And the third column is the number of proofs that we passed. And the ones that were failed were because of timeout issues with the SMT solver. And in the last column is the proofs that would have returned that would have been incorrect. So when we get to a larger program like the WebP image library, we see that same as before, the solver time dominates the runtime, but now we have more proofs that are failing compared to, or like proofs that are not being passed compared to the reference interpreter above, where everything's like 99% plus. In larger programs, you're more likely to have your functions time out, which is why you see numbers in like 89 or 86%. But still, we didn't detect any faulty proofs. And all of the proofs that were not passed were because of timing issues. And when we isolate the proofs and we run them manually, they do manage to pass. And this figure is slightly updated from the one that's available in the paper, because we added some different optimizations to get like a 20 to 50% speed up increase. Okay, so in summary, we are presenting self-certification as another method to writing correct software. We have implemented a refinement checker, various self-certifying optimizations, as well as evaluations against the real-world code. And this is also the basis of future work on verified compilation. In particular, things like secure compilation, inter-procedural optimizations, always more speed optimization, as well as potentially more complex loop unrolling. Okay, and it's also open source at this link. Thank you for your time, and I'm now open to questions.
Thank you very much. Okay, Eric?
Thank you. It was an interesting talk. I was wondering if you could provide a little bit of context of how it relates to Necula's proof-carrying code and Zhang Xiao and others certified binaries. I guess there must be something new about WebAssembly that that makes a distinction, but I didn't quite get it.
Sorry. Is the question asking like how this is related to something like CompCert?
Well, not CompCert generally, but I guess so. Maybe I'll just focus on the proof carrying code. The idea that with your code you include a proof, and that someone can verify before they run your code.
Yeah. Well, I mean, this falls into the same framework, but in particular, this is targeted towards compiler optimizations. But it does fall into the same framework.
Okay, so again, I think about it as sort of falling in the intersection between certified compilation and proof carrying code.
I suppose.
Okay.
Any other question?
Yeah, quick question. Why have an SMT solver involved at all? So if the programmer has to, well, the compiler writer has to generate a proof, couldn't they just provide a certificate from actually the running this SMT solver and just, as you do in PCC in proof carrying code? The idea being is like if you have an NP complete problem, you might as well just solve it once and just, give a compact witness to the verifier.
I guess in this sense, the witness is pretty compact because the backend checker uses symbolic execution. So the proof essentially just says, okay, here in the source and here in the optimized parts, this is what we assert to be equal, and the symbolic execution in the backend would do the heavy lifting, as opposed to having the compiler writer be the one doing the heavy lifting. So symbolic execution can just take these fairly simple proofs, which is say like, this part in the CFG and that part in the CFG should be equal with these formulas, and then propagate all the program semantics to check if they're actually equal. And the reason for the SMT solver was because this was originally developed to we need to encode things like in32 operations, which are glorified SAP problems, and that's why the SMT solver was in the backend.
Okay. Thank you very much. With this, we conclude this session, and the next one will start immediately. Dana.
Okay. Hi. Thanks, Orna. So welcome to the last session for today, Concurrent and Distributed Systems. We're about to have 4 exciting talks. Our first speaker is Christina Peterson, who will present their work on concurrent correctness in vector space. Christina, the stage is yours.
Okay, I'm going to go ahead and share my screen.
Sorry, I can't seem to stop share.
Let me just get this up. Okay, do you all see my screen? Can you all hear me?
Yes.
Okay. My name is Christina Peterson, and I'm presenting my paper, Concurrent Correctness in Vector Space. Concurrent correctness verification has been proven to be a difficult problem. It's been shown that verifying a concurrent history for either serializability, sequential consistency, or linearizability is NP complete, and proving that a concurrent system is sequentially consistent or linearizable is undecidable. The reason that concurrent correctness is so difficult to verify is that there are many possible ways in which the threads can interleave. Consider n overlapping method calls. There's n factorial possible sequential histories. And the worst case growth rate is O of n factorial. So in this case, we have 3 overlapping methods. So 3 factorial is 6, and that gives us 6 possible sequential histories. So many related works have looked at improving verification efficiency, either by generating the possible legal sequential histories more efficiently, or by reducing the number of possible legal sequential histories through use of knowledge of linearization points. The problem is that linearization points can change based on overlapping methods, and efficiently managing legal sequential histories doesn't change the complexity class of verification. So this presents a research question. Can we verify a concurrent history without referencing a legal sequential history? So to answer this question, let's look at the definition of linearizability. a history H is linearizable if it has an extension H prime and there is a legal sequential history S such that L1 is complete H prime is equivalent to S, and L2 if method call M0 precedes method call M1 in H, then the same is true in S. So let's look at these properties in more detail. For the first property, the method calls of history H must respect atomicity and data structure semantics for it to be equivalent to a legal sequential history. And for property 2, the ordering that the method calls take effect respects the required ordering defined by the correctness condition. So for the case of linearizability, it's concerned with method calls taking effect in real-time order. So if a method precedes another method in the history, the same has to be true in the sequential history. So we propose to express correctness properties in vector space. The desired correctness properties that we wish to express include atomicity, data structure semantics, and method call ordering. The way that we achieve this is by expressing method calls as column vectors, where each index in the column vector corresponds to an object and item configuration. So let's first look at atomicity. We'll let item I be an element of a concurrent object O, and then we'll let method call M be represented by a vector V. If M is a producer method and it produces item I and object O, and I is the index configuration, then VI equals 1. And if M is a consumer method that consumes item I and object O, and I is the index for configuration for the object and item, VI equals -1. So VSUM denotes the sum of all the producer and consumer methods. The concurrent history is atomic if for all configurations I, VSUM I is greater than or equal to 0. So if VSUM I is less than 0, that means that a consumer method had consumed an item that did not exist in the data structure. The next property is data structure semantics and method call ordering. So the behavior of the method calls when they take effect is dependent on data structure semantics. The way that we handle this is through a priority system. So if item I has the highest priority to be removed from object O, and index I corresponds to that object and item configuration, then VI equals 1. And if item I has the lowest priority to be removed from object O and item I corresponds to object O and item I, then VI equals 0. But these priority assignments are not static based on the data structure semantics and expected method call ordering. There's many different priorities in between. So the way that we handle this is through a promotion-demotion scheme based on the geometric series 1/2 to the n. So when an item is first produced in an object, it's initially assigned a value of 1. And then if an item is determined to have a lesser priority than another item due to method call ordering and data structure semantics, it's demoted. So for every demotion iteration j, we take v of I and set it equal to vi minus 1/2 to the j, where the domain of j is between 1 and infinity. If we take the sum of this geometric series from 1 to infinity, it equals 1. So the range of the sum of the demotions for an item associated with the configuration I is -1 and -1/2. So it never quite reaches -1 because we never actually reach infinity. So this guarantees that for all configurations I, v of I is greater than or equal to 0. So once an item has been removed from an object, all items previously demoted by I need to be promoted. And so for every promotion iteration j, vi equals vi plus 1/2 to the j. And the domain of j is between 1 and k, where k is the total number of demotions. So let's look at an example. So we have thread 0, which calls NQ7 and DQ8, thread 1, which calls NQ8 and DQ7, and thread 2, which calls NQ9. So the position in the vector, position 0 corresponds to object X item 7, position 1 corresponds to object X item 8, and position 2 corresponds to object X item 9. So looking at the history up to T1, we have the 3 NQ method calls. So NQ7 and NQ8 are both assigned 1 because they overlap with each other. So we don't know which one takes effect first. But the NQ9 happens after the NQ7 in real time. So NQ9 has to be demoted. So it's assigned a 1/2. And if we add the vectors, we get 1, 1, and 1/2. So this history is correct up to this time step. Now we look at time step T2. We have a DQ8. So a DQ8 is assigned a -1. And if we add up the method the call vectors, we get 1, 0, 1/2. Finally, at time step T3, we have DQ7. And DQ7 is assigned -1. But since the NQ7 had previously demoted the NQ9, it has to promote the NQ9 back. So NQ9 is now assigned a value of 1. And if we add the vectors, we get 0, 0, and 1. So this indicates that there's only one item in the data structure, which is item 9. We can also handle reads and writes. Reads are handled similarly. So let V be a vector for a method called performing a read, and let RC be a vector such that RC is a read count for the configuration. When the read is performed in item I and object O, corresponding to position I, we increment RC by 1, and then VI is set to -1/2 to the power of RC. If we take the sum of the reader methods, it's always between -1 and -1/2. And if we let the vsum be the sum of the non-reader method call vectors, then the read is valid if for all configurations I, the ceiling of vsum I plus v of I is greater than or equal to 0. And we take the ceiling because if there's any item, no matter what its priority is, taking this ceiling will make it 1. And so it's going to be 1 if it exists in the object, or 0 if it does not. And since the reads are negative, the reads would cause the sum to be less than 0 if it's reading a non-existent item. So writes perform two things. They consume the previous value held by an item, and they produce a new value to be held by an item. This is handled using priority adoption. So the vector at configuration index of the item's new value is set to the item's priority, and the vector at the configuration index of the item's old value is set to the negative of the item's priority. So when adding the vectors, the vector at the configuration index of the item's old value becomes 0, and the new priority is adopted into that new item's configuration index. So now we're ready to define linearizability in vector space. A concurrent history is balanced if for all configurations I, v sum of I is greater than or equal to 0. So we let t be the time of the method response, and h is the history up to that time t. An extension h prime includes all method calls that overlap with t, since overlapping method calls can affect the outcome. And history h is vector space linearizable. If every method response t, promotion demotion is applied to the method calls in complete h prime, such that M0 happens before method call M1 if M0 and M1 are invoked on the same object, and M0 precedes M1 in complete H prime, and H is balanced up to time T. So the first property just checks the data structure, the ordering, and 2 checks that we're equal to a legal sequential history. We built a correctness tool based on this theory. And we defined the correctness properties in vector space for sequential consistency, quiescent consistency, and quasi-linearizability, in addition to linearizability. And we verified a variety of queues, stacks, and maps. And we compared this to P compositionality applied to a stack. P compositionality has challenges with stacks because a stack can only be partitioned when it's empty. And so that's why it's an exponential trend. Our correctness tool follows an n-squared trend because it requires 2 for loops to iterate through each method and check apply the promotion demotion to all other methods. So quiescent consistency is actually the fastest because we only apply this promotion demotion at the quiescent periods. Sequential consistency takes a little bit longer because we only apply promotion demotion for methods called by the same thread. And quiescent or quasi-linearizability and linearizability take about the same amount of time, or quasi-linearizability takes just a little bit longer because we need an additional for loop to check the distance between to check method call distance. And an interesting observation is that we're able to check the relaxed correctness conditions more efficiently than linearizability. And this is different than what's the results achieved by the existing tools because they have to check all possible legal sequential histories. And so for the relaxed correctness conditions that permit more possible legal sequential histories, they have a larger search space when determining program correctness. So in conclusion, vector space analysis changes the complexity class of the concurrent history verification to polynomial time. The vector space time complexity of O of n squared can be further reduced if the time to check the happens before relation between method calls can be eliminated. And we plan to extend this work to transactional correctness conditions and durable correctness conditions. And that concludes my presentation. Are there any questions?
Thank you, Christina. Feel free to unmute yourself if you have questions. I don't see any on Clouder. In the meantime, maybe I'll ask something. In the experimental slide that you showed, I briefly saw that you had the queues and the stack and the map. Is it the general condition? Does it apply to other data structures?
I'm sorry, what was the question related to other data structures?
So you show for stacks, several stacks, right? And maps and queues, I believe I saw. Does it also apply to other data structures, skip list, whatever, binary search tree?
Okay, right. So yes, sets would qualify as a map without the additional like data field. It's just the item key. So sets we can handle under maps. The one data structure that we haven't extended this to is like account semantics. So if you're trying to actually like maintain different account values, then we can check the account itself, but the value itself, we would have to add additional checks to ensure that the values of that account are correct. So that would require an extension of our logic.
Okay, sounds like interesting future work. Any other questions?
I have just a slight curiosity. I mean, is it in vector space or is it in vector space? Is there a vector, like an algebraic structure over a field? Is that what's underlying some of that?
I'm not sure if I entirely understand your question, but we just represent the method calls as column vectors. So it doesn't really go much deeper than that. We manage method calls as column vectors, and we verify correctness properties by through the sums of those method call vectors. And so that's the general idea.
I was just about the algebraic notion of vector space. So
okay. Yeah, that would be another extension that we would have to look at.
Okay, so thank you, Christina. And our next speaker is Dominic Klomp, who will present their work on verification of concurrent programs using Petri net unfoldings. So Dominic, go ahead.
Yeah, thank you. You can see the slides and you can hear me? Okay. So I'm Dominic, and I will be presenting joint work with Daniel Dietsch, Matthias Heitzmann, Mehdi Nauer, Andreas Podelsky, and Klaus Schätzle. And our paper deals with the verification of concurrent programs using Petri net unfoldings. So I will begin by making that a bit more precise, what kind of problem we are trying to solve. And I will use for this talk as a running example, the example you see on your screen right now. So we get as input this verification problem, where we have a concurrent program here in the middle, which is composed of multiple threads. And we get a specification, which is here given as a precondition postcondition pair. If the variable x is initially 0, then after the program terminates, x is still non-negative. And since this will be our running example, let's look a bit closer at the program itself. What we have here in these two threads is both of them a non-deterministic loop that runs for an arbitrary number of times. And inside the loop, x is incremented by some constant and then multiplied by some constant. And you can see thread 2 is very similar, just it has a slightly different constant. Now you could imagine that we can scale up this program, right? We could add a third thread, which does the same thing, except again, slightly different with a different constant, or an arbitrary number of threads. But what we want to solve when we take as input such a verification problem, we always take a fixed number of threads. So we don't aim to solve this for every n. We just say for a given n, let's say for n equals 4 threads, we want to show that this program satisfies the precondition postcondition pair. And we want to do this in a fully automated way. So what we need, before we get to that, what we have is also an infinite state space, because we have variables here x that range over infinite domains. So in this case, x can be any integer, but we can also work with arrays or the infinite domains. And if we want to verify this program automatically, we need some internal representation for this verification problem. And one thing that one could do, and that is often done in sequential verification, is to take a control flow automaton. So we represent, let's look here at the sequential case where we have our example program, but only a single thread. We represent this as this automaton where we have an initial state. Then we assume that our precondition, x equals 0, holds. We get to the state in the middle and can execute the loop a non-deterministic number of times. And in the end, we assume our negated postcondition. So x is actually, we assume here x is negative, and that brings us to an accepting state. Or here we would also say this is an error state, because if we reach this state, that is a violation of our specification. For a single program, for a sequential program, for a single thread, this is quite a nice representation, but you can maybe guess it. If we go to more threads, it starts to explode. For 2 threads, it's already bigger. For 3 threads, I can barely put it on the slides. But in general, if we go higher, the number of states of this automaton just explodes exponentially. And it should come as no surprise that the verification time also suffers from this. So what we did here, just as an example, is to scale the example program we just saw up to 60 threads. And for each of these 60 threads, we applied a state-of-the-art program verifier, ultimate automizer, and tried to verify that program. And you can see for the first 10 programs, it works quite fine. With 11 threads, we can just about do it, but we have 12 or more threads, we run into a timeout, and you can see here the exponential explosion. Ultimate automizer uses for this a classical algorithm for sequential program verification called trace abstraction refinement, and that uses exactly this control flow automaton representation that we just saw. So what we did in our paper, and what I'm going to show you, is how we adapt this verification algorithm to avoid the state explosion problem in many cases. And the first step to that is that we find a better representation for our program and our verification problem than the control flow automata. And for that, we use patronets, or specifically patronet language acceptors. So if you have seen a patronet before, this should be roughly familiar. You have your places shown here as these circles, and transitions as black squares. And a place can have a token. This is this black dot here you see at the topmost place. Whenever all the predecessors of a transition have a token, which is the case for this blue transition here, we say it's enabled, and we can fire the transition, meaning we take the tokens from the predecessors and put them in the put one token in each successor place. Now, what is maybe not so standard is that we label our transitions with letters from a finite alphabet. So here, the first transition was labeled with A, and we're going to record here at the bottom the sequence of letters that we see. Now we have 2 tokens, and now we have non-deterministically the choice whether we could first fire transition labeled with B, or fire the transition labeled with D, or even the one with F. Let's just see a run of this. So here we choose B. Now we have again 2 choices, C or D. Let's say D and E. And after we fire C, we are again in this situation. We could, of course, go through one or more of the loops again, and we can choose different orderings. So we represent all the possible interleavings of these. This language contains many different interleavings. But for the example, let's say we take the transition labeled F, and we put a token in this place at the bottom here with the double circle. That's an accepting place. And so what does that mean? That means that the sequence of letters, the word we just observed, ABD, ECF, is accepted by this patronet language acceptor. Now, where do programs come into play? Well, we just choose a particular alphabet for this patronet, namely one where each letter looks like a statement. And in fact, what you see here is our example again, our running example with 2 threads. We have here the precondition and a transition that assumes the precondition and puts 2 tokens, one for each thread in these 2 places in the middle. And then we have on the left thread 1 with its loop, on the right thread 2 with its loop, and again a transition with the negated postcondition that goes to an accepting or error place. It's important here that these are just peculiarly looking letters, so we don't take any semantics of these statements into account. This is not, the pattern doesn't have counters or anything, it's just the same as it was before. And if we then take a word of accepted by this patronet, it's a sequence of statements like the one you see here at the bottom. And we call that a trace, or in particular, it's an error trace, because again, we end with a violation of the post condition, so it would represent a violation of the specification. There's one important restriction that we're going to make here in our patronets. We use so-called one-safe patronets. So a place either has a token or it doesn't have a token, but it never has 2 or more tokens at the same time. And that is an important restriction that limits the patronets, but is sufficient for us and makes things more tractable. So to find such an error trace automatically, we use patronet unfoldings, as mentioned in the title, described, for example, by Ken Macmillan in the paper here. And I can't really go into the technical details of this, it's rather complicated, but just to give you a rough intuition, what it does is, well, we really unfold the patronet. So if we have a branch with 2 possible transitions that we can fire when there's a token in the place here, we unfold it into 2 copies of whatever comes below here after the branch. And if we have a loop, we unroll this loop infinitely. Of course, we don't do this only for these very simple branches and very simple loops, but for more complicated structures as well. And that will, of course, yield a possibly or usually infinite patronet with this infinite loop unrolling. But Ken Macmillan's paper gives us sufficient criteria that allow us to stop this unfolding after we have seen a finite prefix of it. And that's called a complete finite prefix, and guarantees that we can answer the question we're going to ask, which is whether or not the language of this patronet is empty. And for us, this is very simple, right? If the complete finite prefix contains an accepting place, then and only then the patronet accepts a word, and we can also extract such an accepted word. So in this way, we can, for example, extract this error trace we saw before. But of course, the verification is not complete, right? We have not considered the semantics of the statements yet, so let's do that. Well, initially we assume nothing, any state could be the initial state. But after we assume that x is 0 and the precondition holds, we know in particular x is non-negative. And if we can then observe that under all these statements of the 2 threads, this is an invariant, right? X remains non-negative at the whole time. And lastly, when we reach the post condition and we know that X is non-negative, but we assume it is negative, we arrive at a contradiction. Meaning this trace cannot actually be executed by the program, because it would yield here, I mean, for this particular trace, you would get 1, 3 times 2 is 6, so you would get 6 is less than 0, which is just not the case. So we say that this trace is infeasible, it cannot be executed, and these assertions here, x greater or equal 0, false, and initially true, is a proof of infeasibility. We use this information to refine our patronet and to subtract traces that we know are infeasible. In this case, this is rather simple. We add these 3 new places and we label them with our formulae, initially true. After we assume x is 0, we know that it's non-negative. And if we then assume that it is negative, we get to a contradiction and we get to false. Note that we here have a connection between our new places and these transitions in the middle, x is 0 and x is less than 0. But we have a construction that allows us to not have any connections with the transitions in the 2 threads. And this is quite important because it reduces the size of the patronet, and in particular, it reduces the size of the unfolding. Lastly, what we actually wanted to do is to subtract these traces, right? So far we have only added new places. To really avoid reaching this contradiction, we just add a so-called blocking place that just never gets a token, and therefore this transition here can never fire, and everything that's dashed here is unreachable in the new Petronet we built. In particular, the accepting place down here is now unreachable. And therefore, through the unfolding, we can again determine that now for this new Petronet, the language is empty. So from this, we conclude for our example program here that the program satisfies its specification. In general, this is a bit more complicated, right? We have a so-called Siga loop where we do this process perhaps multiple times. We check whether it's empty. In our case, that was initially not the case, and we found an error trace. We determined whether it was feasible. In our case, the answer was no. And we extracted these assertions, x greater equals 0, true, false. In general, we construct a finite automaton from these assertions, and we subtract this finite automaton from the Petronet. So the construction you just saw here in the paper, it is explained more generally as a difference operation between a Petronet and a finite automaton. And then we started the process again. We determined that in our example now, the net was empty, and therefore we concluded that the program is correct because all the error traces were successively removed because they were infeasible. If we ever find an error trace that is feasible, of course, then we can conclude the program is incorrect, and we have one counterexample that shows this. So we get to the conclusion. If we look for our counterexample again, we see here again the graph, and you see here at the bottom, I hope you can see it, a blue line. It's almost at the x-axis, because our new approach that uses Petronets scales very well for this example. It scales linear, in fact. And we conclude, so our paper presents a new automated verification technique for infinite state concurrent programs with a fixed number of threads. We do this to avoid the state explosion problem that occurs if we use traditional verification methods for sequential programs. And we achieve this by using Petronets to represent the programs, using Petronet unfoldings and a specialized difference operation between a Petronet and a finite automaton. That concludes the talk. I will be happy to answer your questions if you have any.
Thank you, Dominique. Eric, I see you have a question.
Yeah, thanks for the talk. So one question I wrote in the Clouder is, if you have multiple threads that are executing the same code, then would you still want to restrict it to one safe Petrinets? Or it seems like that would be an opportunity for, yeah.
So our approach would make multiple copies of the same code, and therefore, we would still have a one safe Petronet. It gets a bit more difficult if you have multiple threads with the same code. Just if you have local variables, it becomes a bit unclear, right, which X you're referring to here. So our approach would make multiple, you would just have here X plus 1 on the right as well, and it would still be one safe. Does that answer the question?
Yeah, I think so. I mean, I was also wondering about moving beyond fixed numbers of threads. Did you have any thoughts?
Yeah, we have some ideas on this, and there is some ongoing work on this. But I think there's some extra steps to take, because with just going to not one safe Petronets, on the one hand, it makes many Petronet problems much harder, and it's not quite clear how to give the semantics yet. So what we have, the ideas we have go more in the direction of finding a proof for a fixed number of threads and then showing that this can be generalized to any number of threads.
And can I ask one last question?
We're a bit over, so maybe you should take it offline and we'll continue to the next talk. But thank you again, Dominic, for the great talk.
Okay.
Our next speaker is Elena Stoilkovska, who will present her work on eliminating message counters in synchronous threshold automata.
Let me share my screen.
Yeah.
All right. So, hi everyone, my name is Elena, and I will present our work on eliminating message counters in synchronous threshold automata. And this is joint work with Igor Konov, Josef Wider, and Florian Zuleger. So in this talk, I will introduce an improved way of modeling synchronous fault-tolerant distributed algorithms. And in the literature, synchronous fault-tolerant distributed algorithms are usually specified using pseudocode, similar to the one shown on this slide. This pseudocode describes a reliable broadcast algorithm that tolerates hybrid faults, and you don't have to read and understand what the algorithm does, as I will explain what is interesting for us. So the algorithm is synchronous, and it is run by end processes, which send messages, receive messages, and then perform some action based on the received messages in lockstep. It is designed to tolerate multiple kinds of faults. And for our example, we take the variant of the algorithm that tolerates Byzantine and send omission faults. Byzantine faults are the most severe faults, since the Byzantine processes can act completely arbitrary. While the send omission faults are less severe, and they happen when a process omits to send a message to some of the other processes, but acts as a correct process on the receiving side. So to produce a formal model of this algorithm, which is suitable for formal verification, we can use synchronous threshold automata, which were introduced for modeling and parameterized verification of synchronous fault-tolerant distributed algorithms. And here on the slide, we have the synchronous threshold automaton that captures the process behavior, which is described by this pseudocode. And it resembles a control flow graph where the nodes are called locations and the edges are called rules. So the locations are used to encode the values of the process local variables and the program counter. And the rules are labeled with guards that encode the conditions occurring in the pseudocode and that define how the processes update their local variables. So this particular automaton consists of two parts. One is used to model the behavior of the correct processes, and the other part is used to model the behavior of the send omission faulty processes. And they look the same because the send omission processes, they commit faults only on the sending side, and they act as correct processes on the receiving side. Because the Byzantine faulty processes that we also have in the system act arbitrary, we don't model them explicitly in the automaton, but we capture the effect that their behavior has on the other processes in the system. Okay, now let's have a closer look on how we encode the conditions from the pseudocode into guards on the rules on the, in the automaton. So one thing to note first is that the algorithm is parameterized and that the number of correct and faulty processes depends on the parameters. So here on the slide, we have a condition from the pseudocode, in which a process checks if the number of received echo messages passes a given threshold, and this threshold depends on the parameters. So in order to encode it in the threshold automaton, we can express this check using a guard over the number of received messages of type echo. And this guard, phi1, guards the rule that connects the location V0 and SE. So for example, if we have a correct process, which is in location V0, and it received enough echo messages to pass the threshold, it can use this rule to move to location SE. And the implicit else branch of this condition is captured by the rule phi2, which is the negation of the guard phi1. And so if we have a send omission faulty process in the location OV0, but it did not receive enough messages to pass the threshold, we can use this rule guarded by the guard phi2 to stay in location OV0. So as we can see, coming up with these guards is pretty straightforward, and they can be easily mapped to the conditions in the pseudocode. But there is one problem, and the problem is that in the current definition of synchronous threshold automata, it is not possible to express guards over the number of received messages. And instead, the guards can only be expressed over the number of sent messages. So a user has to manually translate the conditions over the number of received messages from the pseudocode into conditions over the number of sent messages in the synchronous threshold automata. So if you look again at the guard phi1, the following guard is its corresponding guard over the number of sent messages, which is taken from an existing manual encoding of in the synchronous threshold automata framework for the same algorithm. And here, send echo and send omit echo denote the number of echo messages which are sent by the correct and send omission faulty processes. And in the guard, we also have the occurrence of the parameter FB, which is the number of Byzantine faulty processes, and which is used to over approximate the number of echo messages sent by the Byzantine process. So in this manual translation process, a user has to take into account assumptions about the message communication and the faults. And for some conditions that occur in the pseudocode, this is easy, but for others, it is not so obvious. And this manual translation process is prone to human error, as it is not always clear if the user took into account the correct assumptions and indeed came up with the correct guards. So in this context, we have the following questions. Can we automate this manual translation step, but do it in a way that allows us to use existing verification techniques for synchronous threshold automata? And this is the main focus of our work. And I will now give you a brief introduction on a brief overview on our approach. So to model a given algorithm, we start from its pseudocode. We then introduce receive synchronous threshold automata that extend the existing synchronous threshold automata with receive variables, which then count the number of received messages by all processes, and then are used to express the guards. We then define an automated translation procedure that translates the guards over the number of received messages into guards over the number of sent messages. And as a result of the translation procedure, we obtain a synchronous threshold automaton that is a valid input to an already existing parameterized verification procedure, which is based on bounded model checking. Okay, so let's start by looking at what's new in the definition of the received synchronous threshold automata. So first, for each message type M occurring in the algorithm, we introduce a receive variable that counts the number of messages of type M received by a given process. Then also the guards on the rules are expressed over these receive variables. We also define a so-called environment assumption, which is a constraint that it calls the relationship between the number of sent and the number of received messages, and which is and these constraints are imposed by the synchronous message communication and the fault model. So for our example algorithm that tolerates send omission and Byzantine faults, we have the following constraints. So first, the synchronous communication requires that all echo messages which were sent by correct processes are received. And the fault model requires that the number of received echo messages does not exceed the total number of sent echo messages, both by the correct and the faulty processes. And it also requires that the number of echo messages sent by the send omission faulty processes does not exceed the number of send omission faulty processes. Now, observe that this environment assumption defines a relationship between the local receive variables of every process I and the globally sent messages, which means that the local state of the processes is somehow reflected in the global state. So our next goal is to remove this redundant information, and instead of evaluating the guards in the local state, to evaluate them only in the global state. And the idea is, given a receive guard, to automatically translate it to a guard over the number of sent messages, which can be then evaluated in the global state. So this translation is done in two steps. First, we use the environment assumption to strengthen each receive guard. So for example, our receive guard from the previous slide, its strengthened guard is the conjunction of the guard itself and the environment assumption for Byzantine and send omission faults. Next, we use this strengthened guard to define a guard over the number of sent messages by applying quantifier elimination. So what we do is we bound the receive variables in the strengthened guard with an existential quantifier and then apply a quantifier elimination procedure for Pressburger arithmetic. So for our example guard, the result is the following expression that in addition to the guard of the number of sent messages, has additional residual constraints, which were obtained from eliminating the receive variables in the environment assumption. And in the case of this guard, we obtained the same expression that came from the existing manual encoding that we saw a few slides ago. Okay, so by repeating and automating the quantifier elimination step for each guard, we obtain a synchronous threshold automaton where all the guards are now expressed over the number of sent messages. And as a consequence of quantifier elimination, we have that if a receive guard holds in some local state of a process, then the guard obtained by quantifier elimination holds in the global state. So from this, we obtain a soundness and completeness of the automated translation procedure, since we are able to establish a bisimulation between the system of n copies of the receive synchronous threshold automaton and the system of n copies of the automatically generated threshold automaton with no receive variables. And this means that in order to verify the correctness of the system of n automata with receive variables, we can give the automatically generated automaton as the input to the existing parameterized verification procedure. And this is exactly what we did in our experimental evaluation. So we encoded several fault-tolerant distributed algorithms from the literature as receive synchronous threshold automata. And for all of these algorithms, there already existed manual encoding. So we implemented our translation procedure and we used Z3 as backend solver to automate the quantifier elimination step. And from the table, we can see that the translation takes seconds for all our benchmarks. Next, we ran the existing parameterized model checking procedure for synchronous threshold automata, both on the automatically generated automata and on the already existing manual encodings. And this procedure is based on computing the diameter of a system of n automata and then applying bounded model checking. So we noticed that for most of our benchmarks, parameterized model checking performs comparably, but for some algorithms, it performs better on the automatically generated automaton than on the manually constructed one. And in two cases, the step where the procedure computes the diameter timed out for the manual encoding, but produced an output very fast for the automatically generated automaton. So we investigated this further and we checked if all the automatically generated guards imply their corresponding guards in the manual encodings. And we expected this to be the case because the automatically generated guards are the strongest. But in fact, for the two benchmarks where computing the diameter on the manual encoding times out, not all manual guards were implied by the automatically generated ones. And then we looked at these manual guards, which were not implied, and we found subtle bugs, which confirmed that it is difficult to come up with correct threshold automata encodings manually, and that it is beneficial to automatically generate them. So to conclude, in this work, we have reduced the amount of human effort needed to encode synchronous fault-tolerant distributed algorithms. And in this way, we have established a fully automated pipeline that for a given algorithm starts from a formal model that captures its pseudocode given by the receive automaton, automatically produces a formal model which is suitable for verification, and then applies parameterized verification procedure. Thank you.
Thank you, Elena. Any questions? I don't see any on Clouder. If not, because we're a bit over, we'll thank Elena again. And our last speaker for this session and today is Mariana Lazic, who will present their work on a reduction theorem for randomized distributed algorithms under weak adversaries. Mariana, this is yours.
Yes, I will share the screen. Thank you for the introduction. I think you have said everything. I will just add that this is a joint work with Nathalie Bertrand and Josef Wider. And randomization is a natural notion in distributed computing. It's used to prevent attacks, to improve complexity, and also to make impossible things possible. So for example, we know that in asynchronous setting with faults, consensus is impossible, but randomized consensus is possible. And that's exactly the type of algorithms we consider here. And our first steps in verification of such algorithms were done 2 years ago, or 3 already. So when we did verification of randomized consensus algorithms under so-called round rigid adversaries. And since this is the kind of a extension of this previous work, I'll just briefly tell you what was that previous work about. So we modeled these algorithms in probabilistic threshold automata. And so you have seen that actually in the previous talk, but the difference is that now a process can toss a coin. You can see this here as a branching. Then these algorithms have unboundedly many rounds, which means that the process can start in one of the initial states of the first round, then it executes that round. When it reaches the final state of the first round, it moves again to the initial state, but now of the second round, and continues. And also the difference to the previous talk is that this is asynchronous setting, And processes can have different speeds. So one process can be maybe in round 10, maybe very fast process, but the slow one might still be in round 2. So, and this all makes verification very non-trivial. And what we did in that previous work, we only focused on so-called round rigid adversaries, where this cannot happen, that one process is in round 10 and one in round 2. So here, what would happen, that this adversary will first schedule all processes in round 1, and only when everyone is done with round 1, then the round 2 can start. So in this way, you could actually have clear cuts between 2 rounds, and you could isolate a single round and analyze a single round. And that's the way we did this. So this was the trick to verify round rigid adversaries. But what about more realistic ones? So round rigid is not very realistic. More realistic ones would be strong or weak adversaries. And the strong one can just do arbitrary things. So for example, it can schedule a process in round 3. And this process, let's say, tosses a coin. And depending on the outcome, our adversary can schedule a process in round 2 or a process in round 1. So here you see it's not really obvious how would you isolate a single round. Then we have weak adversaries, and they are defined so that the adversary does not see the difference between values in messages, and also doesn't see the difference between outcomes of the coin toss, which means if I don't distinguish these 2 places, then I have to schedule the same process. And this already gives an idea how to isolate a single round. So if I do, every time I see a higher round process scheduled and then a lower round, I'll just try to swap these 2. So first I'll schedule this process in round 2 and then in round 3. And I keep doing this swapping. Eventually I'll have this actually a round rigid adversary. So first round 1 and then round 2 and so on. So this was our main idea. And that's why in this work, we focus on weak adversaries. So the main contribution of this work is that extending these previous results to verify randomized distributed algorithms under more realistic adversaries, so to a broader domain. So what are the challenges? So an adversary in general picks a process and the message that will be delivered to this process. And so previously we were using counter systems. We were counting messages and counting processes, so we didn't distinguish them. So if we want to model this picking a process and picking a message, we have a different setting. So let's say it's more like this. So let's say these are our processes. They're all different. Some of them might be faulty, like this one looks faulty. And then here is our adversary, a postman, who delivers a message to this process. So since this is now a different, we have processes have to have IDs, messages have to have IDs. The first problem is that we have to come up with a new modeling. And that modeling would allow process IDs and message IDs. So actually in this talk, I will not focus on this, on the details of the modeling, but I encourage you to check the details in the paper. But the second thing is now formalizing this idea I mentioned in the previous slide. I want to prove that for every weak adversary, I can always find a round rigid adversary such that these 2 are equivalent. And the idea was exactly to swap 2 transitions, and since this is now done on computation trees, so reduction is again non-trivial, and this is actually what I want to focus here: how to prove this reduction theorem and show that for every weak adversary there is an equivalent round rigid one. So if I want to now follow this idea, every time, so let's say a weak adversary does the following: it first schedules a faster process in round 2, and only then a slower process in round 1. The round rigid one will do the same, just in the opposite order. But if we just naively do this, there might be problems. So let's see what is actually happened here, or might happen. So let's say a weak adversary is first choosing this message that is sent by a pilot when the pilot was in round 1, and it delivers it to the none, who is currently in round 2. And then let's say while executing this step, while tossing a coin, this none will also send the message. And this adversary takes that message and delivers it to this nurse who is currently in round 1. If I want to swap these 2 actions, then the round rigid adversary has to send this message from a none to the nurse, but this message hasn't yet been sent. So it will be sent only when the none moves. So the problem that happens here is that the weak adversary is sending a message from round 2 to a process in round 1. So you can see that this process is receiving a message like from a future, so from a round higher than its own round. And now when we want to move this forward, the problem is that this message is not yet sent. So we want to avoid this receiving messages from the future. So instead of showing that for every weak adversary, I can find a round rigid one, I'll do this in 2 steps by introducing a communication closed adversary. And that adversary actually is defined so that it does not send messages from the future. So it's still a weak adversary, but only sends messages or delivers messages either from the current round or from the past. So now I do this in 2 steps. First, I'll show you that for every weak adversary, I can find an equivalent communication closed one. And I do on an example, just to show you an idea. So let's say a weak adversary is sending this message from a none in round 1 to this process in round 1. That's fine. And then this message to this process, again, from 1 to 1, that's still fine. But then here is a process in round 1 who receives a message from round 2, and we said that might be problematic when we do the swapping. So how do we now construct a communication closed adversaries? So these steps that were fine for us, we just copied them. But if there was a problematic one with a message from the future, this communication closed adversary will remember this, and it will continue with other steps. And let's say after this step, this process now moves to the second round. Now this message is not anymore from the future, it's exactly from that round, and now it's safe to be delivered. So the idea is always if a communication closed adversary sees that it should send a message from future, it should save it for later when this process enters the corresponding round. And since this is only based on swapping here, which is safe, we don't change probabilities of properties, and therefore these 2 adversaries are indeed equivalent. And now I only have to convince you that for every communication closed adversary, I can find a round rigid one, but this was easy because this one doesn't send anything from future. So the only problem here that can happen is that you cannot isolate a single round. So for example, here you can have someone from round 1 scheduled before someone in round 2 before someone in round 1. And in this case, we form round rigid adversary just by swapping these 2. We said since no one receives anything from future, this is just safe to swap. And therefore, if we keep doing this swapping, we will reach a round rigid adversary. And this actually we know how to verify from our previous work. So now in these 2 steps, I've actually shown you that for every weak adversary, I can find a round rigid one that is equivalent to the original one. And just to conclude, so this was the work on parameterized verification of randomized distributed algorithms. And the main 2 contributions are a new model, so a threshold automaton with process IDs, which I did not actually explain in this talk, but you can take a look at the detailed explanation in the paper. And what I actually spent more time in this talk was explaining you this lifting the previous verification result to a broader domain. So now we know that if you want to verify algorithms under weak adversaries, you can actually just focus on round rigid adversaries that are more easier to analyze. And this actually tells us that all these algorithms that we previously verified under round rigid adversaries, now we actually know that they are also correct under weak adversaries. And that would be it. Thank you.
Thank you, Mariana. Any questions? I have a question in the meantime. So you were talking about the weak adversary. What about strong one? Can you show something about this kind of adversary?
No, actually, so here I mentioned strong and weak ones. The problem is that in our work, we always focus on this reduction ideas where we try swapping things. And for weak adversary, this was not so trivial, but it looked like it's possible. But for strong adversary, if you have such a situation, then swapping would not work. So I think this technique would not work on strong adversaries. So it would have to be something completely different for proving. Because the idea is still that a weak adversary doesn't see the difference between these two. So for the weak adversary, this looks like, it doesn't look like a tree actually. It looks like round 3 process, round 2 process. And then it's clear what we are swapping. But in this case, it's really a tree and it's a non-asymmetric tree. So it's not obvious how we would use this.
Okay, thank you. Any other questions? Okay, so let's thank Mariana again. And thank you all for staying for our last session for today. Maybe one of the chairs of VMCAI would like to say something.
The recording has started. Oh, no, it's actually stopped. Thank you very much for today, and thank you to everybody who's been on this historic first day of VMCAI. So, and also please thank you, Grigory, Orna, and Dana for managing the sessions. Yakia, of course, is part of the team with Sharon, who's also still here. That's excellent. So tomorrow we'll continue. Please remember there is we'll start at 1600 hours CET. There's social meetings at 15:30. There's also now an interesting experiment for meeting and mingling on Clouder. So think about it like now we're in the VMCAI room. You can walk out into the hallway. Literally, there are 3 hallways in Clouder, and then participate in a little bit of mingling. So the only thing we need is basically, you know, I don't know, something in our hands, like, you know, I don't know what, but and we had a good chat, you know, in hallway 3 during the break. So I think this could be and is working really well. So as well as it can be as it is. So unfortunately, you can't see this side. This is the current weather we have. So it's too bad. So next time, I think you have to come physically to Copenhagen. But we'll continue tomorrow. So I'll be heading out and see you at the latest tomorrow. Okay? Bye.
Thank you, everyone. Bye-bye.